I'm Panos.
Hi, this is Noe,
Hi, I'm Nick.
I'm Nathan.
and welcome to our post-challenge team review. In this video, we're going to provide an overview on Drone B, our motivations behind this project, the challenges we overcame, and the testings made and what we learned from them. So, without further ado, let's give it to Nick.
There are many factors that motivated our group to construct a drone the way we did. First, sample return and analysis is important for understanding a planet's environment and history. By doing this, we can understand if a planet has always been a barren wasteland or if it can now sustain life. Many of these sample missions are already being conducted. For example, NASA's Perseverance rover uses many sensors such as temperature and magnetic field to understand its surrounding and collect samples for analysis. Another motivator is that by using a drone, this vehicle can reach more hazardous terrains since it is very mobile. But this does bring the limitations such as sufficient lift and battery life. All of these motivators led us to design our drone in the fashion that we did.
Our main objective with our final sensor suite was to include as many sensors as we could. In the end, we were able to include, from left to right, a real-time clock module to line up sensor and video data, temperature sensors, pressure sensor, relative humidity sensor, an IMU to record magnetic field data, as well as two LEDs, one yellow and one red, to let us know if there was a dramatic change in the temperature or magnetic field of the environment we approached. We were worried that the drone itself may interfere with the readings from the IMU, so we chose to have that sensor off-board on the right foot of the drone. If there was a significant change in the field, the red LED would light up to let us know. In addition, we chose to use two temperature sensors, one onboard as a control and the other offboard on the left foot of the drone. This is because in order to get an accurate reading with the temperature sensor, it needed to basically touch the object whose temperature it was measuring. By having one sensor on the foot, we would ensure that the drone would be able to get close enough to an object to take an accurate measurement. We then took the difference between the two sensors to activate the yellow LED and let us know if there was a shift in temperature. The main focus of mounting the drone was to create a solid foundation for the breadboard while staying within the mass limit. Our team's solution to this problem was to use paper clips. These clips were taped to the outside of and fed through the legs of the drone. From there, they were put through two holes on the breadboard. This method allowed us to have a secure base for the board using a very minute amount of mass.
One of the many important aspects of our drone is its sample return capabilities. This drone was outfitted with a bucket system that would pick up samples and then return them to base. The main design of the bucket stemmed from the idea of preventing the loss of a sample because of turbulence. This led us to a bucket attached to the vehicle with pipe cleaners along with a funnel placed on top. This allowed for turbulence to be dampened by the pipe cleaners connecting to the vehicle. Also, the funnel was placed on top in order to trap our samples in the bucket, preventing a loss as well. The pipe cleaners were also offset to allow for a 45-degree angle hang. This allowed for easier sampling since the drone would require less horizontal motion to gather a sample.
As for the recorder, it was necessary to obtain visual data in order to understand where the drone was moving and to ensure that it was traversing through a stable terrain if anything were to happen. To do this, the video recorder was placed next to one of the lateral sides of the drone with an established angle. To connect it, however, with the breadboard, it was required to change the stiff cable with a more flexible one for it to fit in that space.
Then came time for the final test. The drone was flown around a confined course with the goal of collecting data to identify unknown specimens in labeled envelopes, take pictures of the course, and collect samples of both liquid and solid form. Temperature and magnetic field readings were especially key as they were used to identify the type of specimen in each envelope, be it warm or magnetic. From the data, we see that the difference between the onboard and offboard temperature sensors peaked at about 5 degrees Celsius at the time the drone was near envelope B2, and that the magnetic field readings peaked at about 7 to 8 Gauss at the time the drone was near envelope B3. Note that the time on the data and video recording is not aligned due to the fact that the start of the data and video recording were separate by 50 seconds. Unfortunately, the pressure and humidity data readings were not as consistent or stable as those of the temperature and magnetic field. Data analysis of both the pressure and the humidity was difficult since there was no patterns or stability at all. As you can see in the figures, both readings seem to be jumping around randomly. This may have been due to the fact that the sensors themselves had issues with them as they were not working properly in pre-test conditions. Finally, we attempted sample collection with our designed scoop. The scoop was used by flying the drone down to lay the scoop on top of the sample collected, and then further flying downward and forward so the scoop would dig deep into the sample and collect some. This technique was more effective for solid materials but worked reasonably well for liquid as well. Substantial samples were collected for both solid and liquid samples shown in these pictures.
Throughout the construction of the drone, we found ourselves with various design challenges that had to be fixed within a small time frame. The main focus during this entire project was to make sure that the drone could lift as many of the sensors and recorders as possible. This was due to the limited lift capacity of 75 grams. Therefore, instead of using a platform to carry all the different materials, we opted for connecting them with a system of paper clips, which helped reduce the initial weight. Additionally, for the scoop mechanism, the initial design we had was to have a seal on top as well, similar to the picture here shown. Instead, we preferably used a plastic collector held with strings that would further reduce the weight. However, while moving the drone, it would cause a lot of turbulence, so we decided to use pipe cleaners that would hold it better in place. Something to acknowledge, however, from the scoop is that there are various opportunities for improvement, since there are still limitations when collecting the soil and water when conducting the test.
Our group would like to thank Professor Flatten and Billy for their help with our project.
Thank you, Professor Flatten and Billy, for this amazing session.
Yeah, thank you.
Thank you.